Right now, in manufacturing plants all over the world, facility managers are just casually paying hundreds of thousands of dollars a year to run these massive, 100 horsepower industrial machines.
Oh, yeah, constantly.
And the crazy part is these machines are mathematically designed to throw like 95% of their electrical energy directly into the garbage.
Yep, straight into the trash. It's wild to think about.
It really is.
Right.
So, welcome to the deep dive. Today, we are talking about compressed air.
The infamous fourth utility.
Exactly. Right behind electricity, water, and natural gas. And it is entirely invisible. It's absolutely vital to modern manufacturing. And yet, and this is the stat that just blew my mind, in the average plant, up to 50% of the compressed air generated is completely wasted.
Half of it, just gone.
Right. It is this silent, invisible bleed on a company's bottom line.
You know, the paradox of that fourth utility is deeply rooted in just how we perceive it. I mean, think about it. We see water leaking from a pipe, right?
Sure, it creates a slipping hazard. It damages equipment.
Exactly. So it demands an immediate reaction. Or, we can smell a natural gas leak. We physically see the sparks from a shorted electrical wire.
But a compressed air leak.
A compressed air leak just hisses, and it blends perfectly into the ambient noise of a busy factory floor. It's treated almost as an unavoidable cost of doing business.
Rather than what it actually is, which is a highly optimizable, intensely complex thermodynamic system.
Perfectly said.
So, our mission today is to completely decode this invisible utility for you. We are pulling from a massive stack of technical blueprints, engineering guides, and industry white papers from the absolute heavyweights of the compressed air world.
We've got some great data today.
Yeah, we are looking at deep technical data from Kaiser compressors, Quincy compressor, JLL Leach, Infinity pipe systems, and some overarching efficiency guidance from the Department of Energy.
The DOE really lays out the big picture.
They really do. We are going to map out the physical reality of pressure drops, isolate those hidden astronomical costs of system leaks, and break down the exact, proactive routine maintenance strategies you need to turn a wheezing, overloaded system into a highly efficient powerhouse.
Because treating compressed air with the same ruthless scrutiny you apply to your electrical grid, it requires a fundamental shift in how we understand the physics of the system.
A total mindset change.
Right. The moment a facility transitions from just reacting to air shortages to proactively managing air density and flow, the operational savings are immediate.
So let's start that shift right at the source, which is the compressor itself. Reading through that Department of Energy data, compressed air accounts for anywhere from 10 to 30% of a typical plant's total industrial electricity consumption.
Which is a massive slice of the pie.
It's huge. But the RASMEC engineering guide frames the machine in a way that completely alters the perspective. An air compressor fundamentally is not an air machine.
Nope.
It is a heat rejection machine.
That is just a brutal reality of thermodynamics. I mean, when you take a volume of atmospheric air and you force it into a fraction of its original space, you are packing those gas molecules tightly together.
You're squishing them.
Exactly. And so they collide with each other, and they collide with the walls of the containment vessel at a drastically accelerated rate. And that massive increase in kinetic energy, it just manifests as heat.
So the physics basically dictate that roughly 95% of the electrical energy put into the motor of that compressor is rejected to the surrounding environment as thermal energy.
95%. Let that sink in.
It's staggering.
Only about 5% of that massive electrical input actually becomes the potential energy stored in the compressed air that eventually drives the tools.
So if a mid-sized stamping plant is spending, say, $100,000 a year on electricity just to run their compressor room,
$95,000 of that is funding a giant, incredibly loud space heater.
that is nuts.
It inherently makes it one of the most inefficient energy transfers we use in modern industry. You are starting at a 95% energy deficit before the air even leaves the room.
Wow. So every single cubic foot of compressed air that makes it into the distribution piping is incredibly precious.
Highly precious. It represents a massive investment of raw electricity.
Okay, so knowing that massive upfront cost,
Yeah.
it makes the most common human error in any manufacturing plant seem incredibly reckless. I'm talking about the turn it up trap.
Oh, the classic turn it up trap. We see this everywhere.
Let's look at the operational reality on the floor. A worker is at the very end of an assembly line. They are using a pneumatic impact wrench or a paint sprayer, and the tool is sluggish.
It's just not hitting the torque spec.
Right, or it's not atomizing the paint properly, it isn't getting the required pressure. The immediate, almost instinctual human reaction is to walk all the way back to the central compressor room, look at the main discharge pressure dial, and just crank it up.
Because the assumption is a linear relationship, right? The tool needs more pressure, so the source obviously needs to push harder.
Exactly. But the sources, particularly the DOE guidance, are aggressively critical of this reflex. I mean, think about the mechanics of municipal plumbing.
Right, the water analogy.
Yeah, cranking up the central compressor to fix one sluggish tool at the end of the line is mechanically identical to trying to fix low water pressure in your upstairs shower by demanding the city replace the entire town's water tower.
Instead of just taking a wrench and cleaning the calcium buildup off your shower head.
Yes, it's so disproportionate.
And taking that municipal water analogy a step further, if the city actually did raise the pressure of the entire water grid to fix your shower, every single pipe, joint, and valve in every house in the neighborhood would suddenly be under immense, unnecessary stress.
Things would start bursting.
Exactly. The DOE notes that low or fluctuating pressure at the end-use point is almost universally misdiagnosed. It is rarely a symptom of insufficient discharge pressure at the compressor.
Usually the compressor is functioning perfectly fine at its baseline setting.
Right. Raising the overall system pressure is just a systemic Band-Aid applied to a localized wound.
It temporarily masks a restriction downstream, right? Like a crushed pipe or a heavily oxidized valve or a saturated filter.
Yeah, it masks it, but it exponentially drives up the electrical load across the entire facility. The compressor is forced to run longer, it works harder, and it generates way more of that wasted thermal energy.
Just to brute force a marginally acceptable volume of air through a physical bottleneck.
Exactly.
So if the compressor is generating the correct pressure at the source and the tool at the end of the line is starving, we have to look at the space between them.
The distribution network.
Right. We have to map out the physics of what we call the pressure drop. As compressed air travels from the main receiver tank through the distribution network of pipes, hoses, filters, and regulators, it encounters internal friction.
It physically drags against the walls of the piping.
And that physical resistance literally steals pressure.
It does. And the industry benchmarks, which were established by JLL, Leach, and Infinity Pipe Systems, they offer very strict parameters for this.
What are the numbers we should be looking at?
Well, the total allowable pressure drop from the compressor's discharge valve all the way to the final pneumatic tool should absolutely not exceed 10% of the compressor's total discharge pressure.
Okay, 10% max.
Right. And even more stringently, the main distribution pipework, so the primary headers running along the ceiling of the factory, those should lose less than 1.5 psi total.
Wow, just 1.5 psi in the main headers. That threshold is critical to keep in mind because it sets up this golden mathematical rule that appears consistently across the RASMEC, Kaishan, and Quincy technical documents.
It's a formula every single plant engineer should have memorized.
I agree. The rule is, for every 2 psi you increase the compressor's discharge pressure, you increase your energy cost by approximately 1%.
And that scales so aggressively and completely invisibly.
Oh, absolutely. Bumping the pressure up by a seemingly harmless 1 bar, which is roughly 14.5 psi, forces the compressor to draw over 7% more electrical power.
Right. And for continuously running 200 horsepower industrial compressor, that 7% penalty translates to tens of thousands of dollars a year in wasted capital.
Just gone. So, if the massive overhead pipes are appropriately sized and they are only contributing that 1.5 psi of friction loss, we have to isolate where the massive pressure drop is actually occurring. Why are the tools actually starving?
That leads us right to the Quincy compressor research, which introduces an incredibly localized culprit. They call it the dirty 30.
The dirty 30, I love that term. What exactly does that refer to?
It refers to the final 30 feet of the compressed air system.
Ah, okay.
Yeah, so this is that chaotic, localized network of flexible rubber hoses, quick disconnect fittings, point-of-use filters, lubricators, and final pressure regulators that basically bridge the gap from the solid metal puck header down to the actual hand tool.
Quincy's data shows this specific 30-foot zone is just a logistical nightmare. It routinely causes massive pressure drops ranging from 30 to 50 psi.
It's wild. We are talking about 20 times the frictional loss occurring in the hundreds of feet of main structural piping, all localized right at the finish line.
Why is it so bad in those last 30 feet?
Consider the internal geometry of those final components. I mean, take a quick disconnect fitting. It relies on a spring-loaded internal valve to stop airflow when the tool is unplugged, right?
Right.
Well, even when it is plugged in, the air has to navigate around that internal spring mechanism. That creates massive turbulence and restriction.
And then you add a cheap, undersized coiled rubber hose to that.
Oh, the coiled hoses are the worst. The air is forced into a spiral path, so it's constantly colliding with the walls of the hose, losing kinetic energy at every single turn.
And finally, you hit the point-of-use filter.
Yeah. And if that filter hasn't been changed in 2 years, the micron-level mesh is completely occluded with rust scale from the pipes and emulsified compressor oil.
So the air physically has to squeeze through a tiny fraction of the intended surface area.
Exactly. That single neglected filter can easily induce a localized 6 or 7 psi drop all by itself.
Okay, let's run the raw economics on that specific scenario, just to highlight how absurd the turn-it-up trap really is.
Let's do it.
So a dirty point-of-use filter is causing a 6 psi drop. The operator gets frustrated, walks to the compressor room, and cranks the main discharge up by 6 psi to compensate.
It happens every day.
Based on the golden rule, 1% energy penalty for every 2 psi. That is a 3% permanent energy penalty on the entire system.
Right. And the RASMEC guide breaks down the financial reality of this. Let's take a 100-horsepower compressor operating continuously at a conservative rate of 8 cents per kilowatt hour.
Okay?
That machine costs roughly $63,000 a year just in electricity.
So 3% penalty on a $63,000 baseline means the facility is paying nearly $1,900 a year in extra invisible electrical costs.
Yes. They are spending almost $2,000 in pure waste to avoid unscrewing a housing and dropping in a $10 replacement filter.
That is just throwing money away.
Yeah.
It represents a massive failure in operational accounting.
And remember that $1,900 is just to overcome one neglected filter on one tool. Multiply that dynamic by 50 workstations across a sprawling assembly floor, all suffering from various dirty 30 bottlenecks.
The energy penalty compounds so rapidly.
It absolutely does.
But wasting energy at the compressor to overcome a dirty filter is really only the primary consequence. There is a secondary, far more insidious consequence to this.
Oh, the ghost in the machine.
Exactly. When an operator cranks up that central pressure dial, they unknowingly awaken an incredibly expensive phenomenon downstream. The Case IZ and Kaiser sources detail this concept. It's called artificial demand.
Artificial demand is fascinating and terrifying. It is defined as the excess volumetric flow of air, which is measured in cubic feet per minute, or CFM, that is forced out of the system's unregulated uses, simply because the supply pressure was elevated beyond necessity.
Let's isolate the fluid dynamics of that for a second. Let's say I'm looking at a 14-inch leak on an overhead pipe. Or maybe it's an open blow-off nozzle used to clear debris off a machining center.
Okay, pretty common.
If the central pressure is set at 90 psi, a specific volume of air escapes through that orifice every single minute. Now, the physical size of the hole doesn't change.
Right, the hole stays 14-inch.
But if I crank the central compressor up to 110 psi to fix that dirty 30 problem at a workstation on the other side of the building, I have now increased the static pressure pushing against that 14-inch hole.
And the Case IZ report provides the exact mathematical consequence of that action. By increasing the system pressure by just 20 psi, that identical 14-inch opening will now consume 10 additional CFM of air.
10 extra cubic feet per minute just blasting out into the room.
Yes. The velocity of the air escaping through the orifice increases dramatically. Your compressor is now forced to run longer to generate that extra 10 CFM, but your actual production output hasn't moved a millimeter.
You are literally paying to push air out of holes faster.
That's exactly what you're doing. And Kaiser's special report quantifies this across a whole facility. They note that artificial demand typically accounts for 10 to 15% of a plant's total system flow.
Wait, 10 to 15% of all the compressed air generated?
Yep. Which we already established costs tens of thousands of dollars. It's just phantom usage driven entirely by unnecessarily high operating pressures.
So the challenge is really structural, isn't it? Because compressors operate most efficiently when they can generate air at a high, stable pressure and store it in a massive receiver tank.
Correct.
But the tools on the floor operate best at lower regulated pressures.
Right. And historically, plants just allowed the high-pressure air to flood the entire piping network, and they just relied on individual regulators at each tool to step it down.
But that approach exposes every single pipe, joint, and leak to the maximum pressure, which maximizes that artificial demand.
Exactly. But the Kaiser documentation presents the technological solution to this. It's called the flow controller, or frequently it's referred to as a pressure or demand controller.
And this fundamentally redesigns the architecture of the system.
It does. A flow controller is a highly precise pneumatically or electronically piloted valve system, and it is installed directly after the primary air receiver tank.
So it physically severs the system into two distinct zones.
Yes. It isolates the supply side from the demand side. It basically creates a true high-pressure storage reservoir.
Okay, so the compressor can run at its most efficient high-pressure set point, filling the primary tank. And the flow controller sits at the exit of that tank and aggressively meters the air entering the factory's distribution piping.
It functions exactly like a hydroelectric dam on a river.
Ooh, I like that analogy. So the compressor is the rainfall, filling up the deep reservoir behind the dam at immense pressure.
Yep. And in a system without a controller, every time a massive pneumatic stamping press activates downstream, it sends a pressure shockwave back through the pipes.
Which forces the compressor to immediately turn on and essentially make it rain harder to compensate.
Right. It creates chaotic rapid cycling. But the flow controller acts as the dam's automated spillway. When that sudden demand spike hits from the stamping press, the controller's internal sensors detect the microscopic drop in downstream pressure.
And it instantly opens its internal proportional valves just slightly wider, releasing a calculated volume of that stored high-pressure air from the tank into the main header.
Precisely. The distribution piping stays at a perfectly stable, significantly lower pressure.
So the tools get the exact volume of air they need. But because the overall distribution pressure is physically barricaded from the high-pressure storage, that artificial demand is instantly neutralized.
Exactly. The unregulated leaks and open blow-offs stop blasting air at high velocity because they are no longer subjected to the compressor's maximum output pressure.
It just stabilizes the entire aerodynamic profile of the facility.
It really does. And the compressor stops that rapid cycling, turning on and off frantically to chase transient demand spikes, which vastly extends the life of its motor and the internal bearings.
Plus, the tools operate more consistently because they aren't fighting fluctuating supply pressures.
It's a win-win.
Okay, so installing a flow controller locks down the artificial pressure-driven waste, but there is a secondary category of waste that physically bleeds money out of the system, regardless of how perfectly you control the flow.
And this one requires aggressive physical hunting.
Right. We have to talk about the physical leaks in the system infrastructure.
The scale of this problem across the industrial sector is just staggering. I mean, the Department of Energy and the Compressed Air Challenge joint documentation states that the average compressed air system loses 20 to 30% of its total generated volume to leaks.
20 to 30%.
And in older, poorly maintained facilities, that number routinely eclipses 50%.
Let's contextualize that with the thermodynamics we established earlier.
Yeah.
Because only 5% of the electrical energy going into a compressor actually becomes potential air power.
Right.
And the industry average is to lose a third to a half of that precious 5% to physical holes in the piping.
It's completely nuts. The Kaiser and CAC reports run the financial math on this. A single 1/4 inch leak operating at a 100 psi, running constantly at an average industrial rate of 10 cents per kilowatt hour. That costs a facility roughly $20,000 a year.
$20,000 in raw, unrecoverable electrical overhead for a single hole, roughly the size of a pencil eraser.
Yep.
The psychological aspect of this is fascinating to me.
How so?
Well, if a factory floor worker was observed walking up to a scrap bin every single day and tossing 50 pounds of raw, expensive aluminum stock right into the trash, they would be terminated immediately.
Oh, without a doubt. The plant manager would launch a full investigation.
Exactly. But because compressed air is a transparent gas, the visual trigger is missing. Plants just tolerate the hissing. The entire staff walks right past the $20,000 leak every day, and management simply pays the utility bill.
The invisibility makes it deeply insidious. But the CAC documentation points out an even greater hurdle, which is the acoustics.
Right, you can't always hear them.
Human hearing is a fundamentally inadequate tool for leak detection. A leak costing a facility $200 a year in wasted energy is entirely silent to the human ear.
Completely silent.
Yeah, and a leak costing $800 a year might generate enough velocity to be felt if you pass your hand directly over it, but the frequency of the sound it makes is completely drowned out by the ambient low-frequency roar of surrounding machinery.
You just can't compete with a stamping press. So the Ford Woodhaven stamping plant case study that's highlighted in the compressed air challenge sources is honestly the perfect blueprint for solving this.
They did an amazing job. They realized they couldn't use their ears, so they deployed technology, ultrasonic acoustic detectors.
Tell me about the physics behind ultrasonic detection.
Well, it relies on fluid dynamics. When a pressurized gas moves from an area of high pressure inside the pipe to an area of low pressure outside the pipe, say, through a microscopic crack or a failing thread seal, it transitions from laminar, smooth flow into highly turbulent flow.
And that turbulence generates friction against the edges of the crack.
Exactly. That friction emits high-frequency acoustic waves. These are frequencies far above the threshold of human hearing, typically in the 38 to 42 kilohertz range.
Okay, so we can't hear it. But why is that frequency range so useful?
The beauty of high-frequency sound waves is that they are highly directional and they do not penetrate solid objects well. They don't bounce around the room like a low-frequency machine rumble does.
So an auditor basically walks the floor with a handheld ultrasonic detector and a pair of industrial headphones.
Yep. The device features a highly sensitive microphone tuned specifically to those upper frequencies.
And it captures the ultrasonic hiss of the turbulent leak. And it uses a process called heterodyning, right?
Right, heterodyning. It translates that super high frequency signal down into an audible frequency that the auditor can actually hear through the headphones.
While simultaneously displaying the decibel intensity on a screen.
Exactly. So it allows the maintenance team to stand 20 feet below an overhead pipe rack, point the detector upward, and pinpoint the exact failing valve right amidst the deafening noise of a stamping press.
That is incredible. And the execution at that Ford Woodhaven plant was incredibly methodical. They didn't solve their air shortage by purchasing a new $1 million compressor.
Nope. They formed a dedicated internal leak detection team.
They systematically mapped the plant with ultrasonic detectors. They targeted the massive pneumatic die cushions on their stamping presses, replacing deteriorated internal seals. They rebuilt the regulators and lubricators in all those dirty 30 zones we talked about.
And by aggressively mitigating those physical leaks, they fundamentally altered the demand profile of the plant. They were actually able to lower their main header pressure by a mere 5 psi.
Just 5 psi. And the cumulative payoff of repairing the seals and dropping the pressure just 5 psi was an 18% reduction in total plant air usage.
18%.
Yeah, that massive drop in demand allowed the engineering team to walk into the compressor room and completely shut down one of their massive 800 horsepower rotary screw compressors.
It took it entirely off the grid.
That single operational change saved the Woodhaven plant 7.9 million kilowatt hours of electricity. That equates to a staggering $400,000 in savings every single year.
It is the ultimate example of reclaiming lost capital. However, finding the leaks, locking down the pressure with flow controllers, and cleaning up the distribution piping, all of that only optimizes the demand side of the equation.
Right, we still have to talk about the supply side.
Exactly. Because at the supply side, the compressor itself is slowly degrading mechanically. It will cannibalize all of those energy savings. Protecting the machine requires managing its ultimate nemesis.
Heat. We return to the heat rejection machine.
We do.
The RASMAC engineering guide draws a very sharp, very critical distinction regarding routine maintenance here. If a facility manager simply follows the manufacturer's provided maintenance manual, they are executing a schedule designed purely for machine longevity.
Right. The manufacturer's primary goal is to ensure the compressor doesn't suffer a catastrophic mechanical failure during the warranty period.
But the guide stresses that running reliably is not the same as running efficiently. To achieve maximum energy efficiency, the maintenance strategy must be far more proactive and analytical.
Absolutely. We have to analyze the heat exchangers. Industrial rotary screw compressors utilize a series of cooling mechanisms to manage the intense thermal load of compression.
Like intercoolers.
Yes. Multi-stage compressors utilize intercoolers. An intercooler is a heat exchanger positioned between the first and second stages of compression.
Why do we need to cool the air halfway through the process? I mean, isn't it just going to get hot again?
Because of molecular density.
Yeah.
When the first stage compresses the atmospheric air, it gets incredibly hot. And hot air expands, the molecules push apart.
Okay, so it takes up more space.
Exactly. Trying to force that hot expanded air into the second stage requires significantly more mechanical force and therefore more electrical energy than compressing cold, dense air. The intercooler strips the heat out of the air before it enters the second stage.
So if the fins of that intercooler are coated in a layer of insulating factory dust or, vaporized machining coolant,
the heat transfer fails, The second stage works exponentially harder, and your power consumption skyrockets.
Makes perfect sense. And then, after the final stage of compression, the air passes through the aftercoolers before exiting the machine.
Right. The aftercooler is responsible for dropping the temperature of the finished compressed air down to a manageable level.
And the benchmark there is that a fully optimized, deeply cleaned aftercooler should discharge compressed air that is no more than 15 to 20 degrees Fahrenheit above the ambient temperature of the compressor room.
Yes, that 15 to 20 degree delta is crucial because this directly impacts the moisture content of the air. Hot air can hold a massive amount of water vapor in suspension.
Like humidity on a hot summer day.
Exactly. As the aftercooler drops the temperature of that air, it crosses the dew point. The air can no longer hold the water, and it physically condenses into liquid right inside the machine.
So if the aftercooler's fouled and running hot, it fails to condense that water. It sends a massive wave of superheated, fully saturated air down the pipe.
Which completely overwhelms the downstream air dryers, pushing liquid water directly into the factory piping.
That sounds like a nightmare. But beyond cooling the air, the most critical thermal management system in a rotary screw compressor is the oil.
Oh, the oil is everything.
For you listening and visualizing the machine, the air end is the beating heart of the compressor. It consists of two massive, interlocking helical screws, the rotors that spin at high speeds, mashing the air into a smaller volume.
And those rotors do not actually touch each other. They are sealed and lubricated by a continuous flood of highly specialized synthetic oil.
The RASMEC guide specifies an incredibly unforgiving Goldilocks zone for the temperature of this oil. It must be maintained exactly between 180 and 185 degrees Fahrenheit.
The chemistry of that synthetic oil is incredibly sensitive to thermal excursions. If the oil cooler becomes restricted and the internal oil temperature creeps just slightly above 190 degrees Fahrenheit, the chemical breakdown accelerates rapidly.
Just a 5-degree jump to 190 ruins it.
Yep. The oxidation rate skyrockets, and the lifespan of that extremely expensive synthetic fluid is instantly degraded by 25%.
The sources mention the development of varnish at high temperatures. What exactly is happening chemically when that forms?
So when the oil surpasses 200 degrees, the base hydrocarbon chains begin to shear and break apart. The oil oxidizes, creating highly acidic byproducts.
And those byproducts precipitate out of the fluid.
Exactly. They precipitate out and bake onto the internal metal surfaces of the air end and the oil coolers. It forms a thick, sticky, incredibly hard lacquer known as varnish.
And varnish acts as an insulator, right?
Yes. So it further destroys the cooler's ability to reject heat, creating a thermal runaway loop. And it also coats the internal bearings, destroying their microscopic tolerances.
The intuitive reaction to hearing that heat destroys the oil is to just run the machine as cold as possible.
Naturally.
But the RASMEC data explicitly warns against this.
Because running the oil too cold is just as destructive. If the thermostatic bypass valve fails and the oil temperature drops below 180 degrees Fahrenheit, the oil doesn't get hot enough to reach the boiling point of water.
And like we said, atmospheric air is full of humidity. When it is compressed, that humidity is squeezed out.
Right, so if the oil is below 180 degrees, the liquid water does not vaporize and vent away. Instead, it emulsifies directly into the oil.
It creates this milky, highly destructive sludge.
Exactly. And water has absolutely no load-bearing film strength. When that water-laden oil is injected into the high-speed bearings supporting those massive steel rotors, the water flashes into steam under the pressure.
So the metal-to-metal contact is completely unmitigated.
Yes, and the bearings spall and fail. That is the catastrophic death of the air end, requiring a massive capital expenditure to replace.
So just relying on the hours run meter on the control panel to schedule an oil change is completely inadequate because it doesn't account for these thermal spikes.
Not at all. The proactive maintenance strategy demands predictive chemical testing. Maintenance teams must draw oil samples regularly and utilize total acid number, or TAN, testing kits.
The TAN kit measures the exact concentration of acidic oxidation byproducts in the oil.
Exactly. It provides a highly accurate numerical value of the oil's chemical degradation. By charting the TAN value over time, a facility manager can perfectly predict exactly when the oil is beginning to break down.
And then schedule a fluid change weeks before the acid levels are high enough to generate varnish or attack the bearing surfaces.
Proactive, not reactive.
I love that. Okay, so we've optimized the coolers and the oil chemistry. The final piece of the mechanical puzzle is the actual ambient air the compressor is breathing in. The fundamental rule from RASMEC is that compressors demand cold, clean, dry air.
Always.
So the inlet air filter is the first and arguably most important line of defense.
Remember the physics of compression we talked about? It takes more electrical energy to compress hot, thin air or air that is fighting to get into the machine.
So if the massive paper inlet filter is clogged with factory particulate, the compressor is effectively trying to sprint while breathing through a cocktail straw.
A huge vacuum is created in the inlet housing.
The required maintenance protocol here is strictly quantitative. I just look at the filter and guess if it is dirty. You have to monitor the inlet differential pressure gauge.
Right, because that gauge measures the exact difference in atmospheric pressure between the outside of the filter and the inside of the intake valve.
And if that differential gauge reads above 2 to 3 psi of restriction, the filter is occluded and must be replaced immediately.
Absolutely immediately. Letting that gauge climb past 3 psi triggers a direct 1 to 1.5% energy penalty on the total electrical draw of the machine.
Again, we are back to the tragic economics of the Dirty 30. A facility will unconsciously spend thousands of dollars in invisible electrical waste over 6 months, just to delay spending $50 on a new paper inlet filter.
It is entirely self-defeating. And, that clean air, once compressed, creates one final maintenance hurdle we have to touch on: condensate.
Oh, the water.
Yeah, when a massive 200 horsepower compressor sucks in humid ambient air on a rainy spring day and compresses it to 100 psi, it concentrates the water vapor immensely.
And as the aftercoolers and downstream refrigerated dryers drop the temperature of that air, massive volumes of liquid water physically drop out of the airstream.
We are not talking about a few drops either. A large system can generate dozens of gallons of acidic liquid water every single shift.
Dozens of gallons. If that condensate is not aggressively managed and gets pushed into the main distribution headers, the consequences are catastrophic for the plant infrastructure.
Oh, it's terrible. I mean, imagine a facility located in a cold climate. Water accumulates in an overhead pipe running near a loading dock door, and it freezes overnight.
The ice expansion physically bursts the steel pipe, shutting down the entire plant.
Exactly. And in the summer, that same water sits in the low points of the carbon steel piping, initiating aggressive internal oxidation. The pipes rust from the inside out.
And that iron oxide scale eventually flakes off, travels down the pipe at high velocity, and basically acts like sandblasting media inside the pneumatic tools and directional valves, totally destroying them.
The traditional antiquated method for removing this water was the manual crack valve. A maintenance worker would slightly crack open a ball valve at the bottom of the receiver tank, allowing a constant hiss of air and water to spray out onto the floor 24/7.
Which, based on our leak math from earlier, is literally blowing $20,000 a year straight into a floor drain.
Yep. Then the secondary evolution was the timer drain, a solenoid valve programmed to open for exactly 5 seconds every 10 minutes.
But the flaw there is that humidity changes, right?
Exactly. On a dry winter day, there is no water, but the valve still opens every 10 minutes anyway, blasting pure, expensive, compressed air into the room.
So what's the solution? The ultimate efficiency standard highlighted in the engineering guides is the installation of zero-loss condensate traps.
A zero-loss trap is a highly engineered, demand-driven valve. It utilizes an internal capacitive sensor or an internal float mechanism tied to a magnetic pilot valve.
So it only opens when there's actually water.
Right. The valve remains completely sealed until a specific predetermined volume of liquid condensate accumulates in the reservoir. Once the sensor detects the water level is high enough, it triggers the valve to snap open, rapidly discharging the liquid.
And crucially, it snaps perfectly shut while there's still a small margin of water left covering the exit orifice,
ensuring that absolutely zero compressed air escapes into the atmosphere. It's brilliant.
We also have to maintain the specific machines responsible for dropping that temperature and forcing the water out in the first place, right? The refrigerated air dryers.
Yes, the refrigerated dryer operates on the exact same thermodynamic principles as a commercial air conditioning unit. It uses a chemical refrigerant circuit to chill the incoming compressed air down to roughly 38 degrees Fahrenheit, basically wringing all the moisture out before the air enters the factory.
And the critical maintenance point here involves the condenser coils on that refrigeration circuit. Just like the AC unit sitting outside a house, the dryer must reject the heat it pulls out of the air.
If the thin aluminum fins of the condenser coil become packed with dust, or cardboard fibers from the packaging line, or welding smoke, the heat transfer coefficient plummets.
The refrigeration compressor overheats, the cooling circuit fails, and the dryer simply stops chilling the air.
And the dew point spikes, and that massive wave of moisture bypasses the dryer entirely.
You know, the interconnected nature of this entire utility is just astounding. If we trace the causality backward, a catastrophic financial bleed can start with something laughably small.
Oh, absolutely. Walk me through one.
Okay, say a maintenance tech skips cleaning the dust off the condenser coil of a refrigerated dryer in the corner of the room.
Okay, happens all the time.
Because the coil is insulated by dust, the dryer runs hot and allows moisture to slip past. That liquid water travels hundreds of feet down the main header and settles into a point-of-use regulator in the dirty 30 zone of a critical assembly machine.
And the water causes the internal spring of the regulator to rust and seize?
Creating a severe pressure bottleneck.
Right.
The tool operator notices the torque on their impact wrench is weak. They abandon their station, walk to the compressor room, and crank the main discharge pressure dial up by 10 psi to overcome the rusted regulator.
And that 10 psi increase triggers a 5% increase in the compressor's electrical consumption.
Exactly. Simultaneously, that elevated pressure surges through the entire plant, subjecting 50 microscopic, undetected leaks in the overhead pipes to higher static pressure.
So the artificial demand skyrockets, forcing 15% more air out of those leaks.
And now, the 100-horsepower compressor is running continuously at maximum capacity, generating immense thermal loads.
The oil temperature spikes to 195 degrees, accelerating the oxidation and creating varnish. The tan numbers soar.
And suddenly, because a single layer of dust was left on a cooling coil, the facility is bleeding thousands of dollars a month in invisible electricity. The lifespan of the compressor oil is cut in half, and the air end bearings are ticking toward catastrophic failure.
It perfectly illustrates why treating compressed air as an afterthought is so incredibly dangerous. It requires a holistic, deeply analytical approach to system architecture.
Which brings us to the ultimate summary of our deep dive today. If you want to transform the fourth utility from a massive financial liability into a controlled, highly efficient asset, it requires abandoning the reactionary mindset.
You have to stop treating the discharge pressure dial as a universal problem solver.
Yes, you must map out the friction and eliminate the localized bottlenecks hiding in the final 30 feet of your network, your dirty 30.
You must sever the high pressure supply from the low pressure demand by installing precision flow controllers, eliminating the pressure fluctuations that drive all that artificial consumption.
You have to accept that human hearing is useless for efficiency audits and equip a dedicated team with ultrasonic acoustic detectors to hunt down the microscopic turbulence draining your capital.
And critically, you must treat the thermodynamics of your compressor with immense respect. You are managing a heat rejection machine.
You must proactively monitor the inlet differential pressure, track the chemical degradation of the synthetic oil using TAN testing, clean the heat exchangers relentlessly, and install zero-loss traps to manage the massive volumes of condensate.
Executing those strategies transitions a maintenance department from just putting out fires to actively generating profit for the facility.
Before we wrap up, our expert has a final, incredibly provocative thought regarding the future of manufacturing, drawn from a subtle, almost philosophical point hidden deep in the compressed air challenge documentation.
Yeah, as we analyze the immense effort required to optimize these systems, we have to return to that fundamental, unavoidable truth of thermodynamics. 95% of the electrical energy put into the compressor is instantly lost as heat.
It's just inherently wasteful.
Exactly. The system is built on a foundation of massive inefficiency. Because of this, the CAC authors suggest that sometimes the absolute most effective way to optimize an inappropriate use of compressed air is to simply remove it from the pneumatic system entirely.
Just get rid of it.
Right. They strongly advocate for auditing the floor and replacing pneumatic paint agitators with direct drive electric motors, or swapping out highly inefficient air-driven assembly tools with modern, high-torque, battery-operated DC electric tools.
Which raises an existential question about the factory of tomorrow.
Exactly. As industrial battery density improves and brushless DC motor technology becomes cheaper, lighter, and more powerful, the reliance on pneumatics is being seriously challenged.
Will the ultimate efficiency hack for the factory of the future be to eliminate the fourth utility altogether?
Are we slowly moving toward a purely electric manufacturing environment, rendering the massive, leaking, highly complex networks of compressed air piping completely obsolete?
It is a fascinating trajectory to consider the next time you walk the floor and hear the faint, expensive hiss of escaping air.
Definitely something to think about.
From the murky, reactionary chaos of the turn-it-up trap to the precise, thermodynamically balanced engineering of a perfectly sealed facility. Until next time, keep diving deep.